All right, class, today we're going to talk about VSEPR, VSEPR, valence shell electron pair repulsion, and Lewis structures. This information can be found in Chapter 3 of your textbook. So we're going to begin with characteristics of covalent compounds, VSEPR, and Lewis structures. So the molecular mass is the mass of a molecule, which is the sum of the masses of all of its atoms. And so as a simple example, let's do H2O, water. So if you look at the periodic table posted in Unit 3, you would notice that H weighs 1.01 if you do the correct rounding. So there's two of them, and it's because that subscript tells me that. And then the oxygen is 16.0. We'll just round that 15.999 to a 0 and make that 16. And then you get 18.02, and we'll call that units. And so that would be the molecular mass. So what I did is I added up each individual atom in that molecule to get a total weight. Valence shell electron pair repulsion, VSEPR, is the general concept that estimates the shape of a simple molecule. So we're talking about the shape, and it's based on this, okay, that electrons tend to repel each other because they are negatively charged. Now consider this example. Let's say I had NH3, which is a molecule known as ammonia, but I wanted to actually represent it how it might look in solution, because we know that there's no such thing as a subscript in solution. There's no 3 hanging out in the beaker or flask. Instead, it takes on a particular shape, and I would say that this is the wrong shape, and I'll tell you why I think that. It's because each covalent bond is composed of 2 electrons. Okay, but we just show it as a line indicating 2 electrons. And then over here you have this non-bonding pair of electrons hanging out to fulfill the octet, making this a stable molecule. Now, notice that this particular nitrogen-hydrogen bond is right next to this particular nitrogen-hydrogen bond, each of which have 2 electrons per bond. They are going to repel each other. They don't like being there. And the same thing goes for there, and then the same thing goes for there. Electrons don't like being near each other, just like the same ends of 2 different bar magnets don't like being near each other. They repel, they do not attract. And so what's going to happen is this molecule is going to find the lowest energy conformation at which everything is spaced out as evenly as possible, giving itself a shape. And so the best spacing for ammonia takes on what's called the trigonal pyramidal or trigonal pyramidal shape. And notice that in each case, they are about as far away from each other as they can be, and also from this non-bonding electron pair. Okay, and so that's the basis of the VSEPR, valence shell electron pair repulsion, and now you can kind of see where this theory gets its name. We're looking at the valence shells and how the electron pairs repulse each other in order to give it a shape or repel each other. And so electron groups are any group around the central atom or lone pair or atom. Okay, lone pair sometimes is non-bonding electrons. It's the same exact thing. And so the way we look at electron groups is it is any group around the central atom. And so if you look at the molecule of water shown right here, what you'll notice is that O is the central atom. Hopefully that's obvious. And then we have really 4 groups around it. We have one group here that we might call an H, one group here that we might call an H, a grouping here that we'll call 2 non-bonding electrons, because electrons that are non-bonding tend to occur in pairs, and then one right there. So 1, 2, 3, 4. So we're going to look down here and find 4 electron groups. And it already tells you that the bond angle of this molecule is 109.5. Now, given that that is true, we need to figure out what the shape is. Now, the question is how many outer atoms to lone pairs are there? And if you look, there's 2 sets of lone pairs and 2 sets of atoms. So we're looking at this one right here, 2 outer atoms, those 2 H's, about that central atom, and 2 lone pairs. So the shape of this molecule is bent. Okay, water is considered a bent molecule, and that's the reason why it's actually considered a polar molecule, because this are polar bonds, but they don't cancel each other out because of the bent nature or the bent shape of the water molecule. Okay. Here are some other important shapes you might see is linear, trigonal planar, tetrahedral, trigonal pyramid or trigonal pyramidal, or bent. These are some important shapes for this class. Linear is one you might see actually with, say, acetylene. Okay. Now, I know that because let's just act like this is my central molecule right there, or central atom. Notice that it only has two groups around it, one being that H and one being that part. Okay, so there's two groups and no lone pairs. If you were to look at this table from the previous slide, sorry, somehow it cut out on me. This table from the previous slide, which you'll notice, is that it has two groupings. Which puts me right there. And it has two outer atoms and no lone pairs, so this is called linear. If I were to draw this one, molecule known as formaldehyde, notice that this C is my central atom, and it has three groupings around it, no lone pairs. Three groupings, no lone pairs, gives me this one right there, so that's a trigonal planar. Let's see, what's another example? Tetrahedral, that's like methane, CH4. So here's my central atom right here. And it has four groupings around it, 1, 2, 3, and 4. And so with four groupings, no lone pairs, that gives you tetrahedral. And we've done the trigonal pyramid or trigonal pyramidal with the ammonia. And that should get us everywhere. Bent is water. Okay, so if you wanted examples, this one could also be CO2. You can look up the structure of CO2, carbon dioxide. Trigonal planar, formaldehyde is a good example if you just wanted to Google these. Tetrahedral, methane. Trigonal pyramid, ammonia. Bent would be water. Okay, Lewis dot structures or Lewis structures, another super important concept in this class. So the way you draw Lewis structures is I might give you, or your instructor might give you a molecule and they ask you to construct a shape, or what's the proper shape of this molecule. And so what you do is you need to sum up the valence electrons from all atoms, put this number aside. So let's try NH3, ammonia. So how many valence electrons does nitrogen have? Hopefully you're getting skilled at this. You should come up with 5. How many valence electrons does H have? 1. But there's 3 H's in this molecule, so we're going to say 3. There's only 1 nitrogen. And so we have 8 total valence electrons to work with. Then you got to ask yourself, what would be the most reasonable central atom of this particular compound? Would it be something like an H, something like that? I don't think so. I think the more appropriate way to position this molecule would be to put the nitrogen in the center and then position the 3 H's around it, because you know that H is like 1 bond and nitrogen prefers 3. Now, we need to make the outer atoms have a full octet first. There is, of course, exceptions to this, and we know that hydrogen doesn't need a full octet because it can only get to the, it's a 1s. And so being a 1s means that it's fine with just 2 electrons. So it's not an octet, it's fine with 2. 2 is the maximum hydrogen can have. So does hydrogen have 2? Well, yeah, 1, 2, 1, 2, and 1, 2. So we're good on our outer atoms, okay? The hydrogens are full. Now, does the nitrogen have an octet? Okay, no, it doesn't. It only has 6 electrons around it. 2, 4, 6. So it might be good to throw a lone pair of electrons or non-bonding electrons on it to give it 8. And then in order to judge if this is complete or not, we need to tally up to make sure the total electrons found in this structure equals that number. And let's see, we have 2, 4, 6, and 8. And so that's good. And then you would go look at your diagram to see if you drew it properly in a trigonal pyramid. And then here is number 5, calculate the formal charge represented for each atom. Formal charge is simply number of valence electrons minus number of non-bonding electrons minus number of bonds. And so just to quickly do that, let's just take this H for example. Number of valence electrons is 1 valence electron according to your periodic table, minus number of non-bonding is 0, minus number of bonds is 1, so that equals 0. And so that doesn't have a charge on it whatsoever. The nitrogen has 5 valence electrons, minus 2 non-bonding, minus 3 bonds equals 0. So there's not a charge located on this structure, so we drew it correctly. That's how you calculate the formal charge. So let's try some Lewis dot examples, okay? H2O. So how many valence electrons do we have for H? So there's 1 valence electron times 2 H's equals 2. How many valence electrons does oxygen have? You should come up with 6, and there's only 1 oxygen. So we need to come up with 8 total valence electrons. So we're going to now determine the central atom. Maybe put the other 2 around it. The H's have 2 electrons each, so they are complete. And then the oxygen only has 4, so we need to add 4 more to make it 8. Check your formal charge, and you should find that it has 2, 4, 6, 8 total around it. And I just mentioned formal charge, but I didn't do it, so let me show you, especially around the oxygen. So oxygen has 6 valence electrons, minus number of non-bonding, minus number of bonds, equals 0. So oxygen has no formal charge, neither do the hydrogens. BF3 is a tough example because whenever you get to group 3A in column 13, the periodic table, the one that begins with boron and has aluminum under it, those atoms or elements tend to want 6 electrons. They're perfectly fine with 6. They're not going after an octet. So that's why I wanted to show you this example really quick. Keep in mind water is bent according to VSEPR. So B should be our central atom. Let's put our F's around it. I forgot to total the valence electrons. So boron should have 3 valence electrons, and there's only 1 boron. Each fluorine has 7, and there's 3 of those, so 21. So we should have 24 total. And so now I've positioned. So next you want to ask yourself, in this particular structure that I just put a box around, does it have an octet around every fluorine? And the answer is no. And so let's make it. So each one has 2 already. 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. And we're also good because I told you in a previous video that halogens prefer 1 bond. And so there you have it. They have 1 bond, and they have an octet. Now, where are we at in terms of our valence electron total? So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we're done, and that's largely the reason boron and aluminum are fine with only having 6 around it, is because of this. Okay, there's just no valence electrons left. Okay, so that's the Lewis structure of BF3. Okay, and so let's finish off with let's do CO2 because that's a little bit tricky. We'll go over here for CO2. So let's determine the total number of valence electrons. So carbon would be 4 valence electrons times, and there's only 1 carbon equals 4. Oxygen has 6 valence electrons, and there's 2 of those, 12. So we should come up with 16 total valence electrons. Now let's pick our central atom, C. Let's put O's around it. Okay, I'm just going to draw it a random shape for now. And now let's make everything have an octet, okay? Okay, well, so now oxygen has an octet, and carbon has an octet. Well, oxygen, let's count up our total electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Uh-oh. It says that we can only have 16 total, and I just counted 20. So we must have done something wrong. And so that's why you have to go back to the drawing board and try something else. Now, I had told you that in a previous lecture that oxygen, that particular column, prefers 2 bonds, and that carbon prefers 4 bonds. And so what happens if we just make oxygen have 2 bonds each and now try to fulfill the octet rule? And notice whenever I did that, that carbon now has 4 bonds, which it tends to like. And when I say like, it just means that it's neutral when it has that, okay? Now let's check this out. Making that adjustment, 2, 4, 6, 8, 10, 12, 14, 16. So now we have the right structure. It's just in the wrong shape. And so really CO2 should be drawn linear. Also want to warn you that in Lewis structures, you have to show all electrons, okay? So it's important to show these non-bonding electrons when drawing Lewis structures, okay? Just to try out, because I didn't go over this one with you, C2H2 should give you this structure. And go ahead and try out the formal charge on those carbons. I didn't show you how to do it, but you should get 0 for all of those. Hope this helped. Bye-bye.